I would like to talk about quantifiers and their negation because this comes up a lot in mathematical proofs, even with vector spaces. This is the universal quantifier, and the way we read this is that for all. And this is the existential quantifier, and the way we read this, there exists. There are, of course, many other logical notations. Some of them I'm not going to use. And the main reason actually I want to use the quantifier notation instead of the words for all and there exists, because in fact it makes work easier many times. You can search YouTube videos, for example, with tutorials about quantifiers and their negations. Those are very general, and I would like to talk about these in relation to the homework assignments and also to this class that we are working in. So the general rule is that if you want to negate something, negation, you can also say with words that it is not the case that, and then the mathematical statement that you want to negate, or simply we just say that not, or it is not true that something is true, or some statement. The notation for the negation is usually this symbol in mathematics. I think I've also seen actually, instead of a longer horizontal sign and a shorter vertical sign, I've seen the opposite, where the horizontal part is shorter than the vertical one. And has this notation, and the or has this notation, but I don't think I want to use that. Some people love not using words in mathematics. Of course, you should know that the negation of and, not and, is equivalent to saying or, and the negation of or is and. Many times we have implication. So statement could be something that says px is statement, and another statement could be qx. And when we say that if p of x, then q of x, very shorthand mathematical notation would be that p of x implies q of x. There is a hidden universal quantification here. It is actually better to write, in my opinion, this with the quantifier and to say that for all x, p of x implies q of x. And with the universal quantifier, for all x, p of x implies q of x. That means if p of x is true, then q of x is also true. The negation of that, first of all, let me write it this way, that what we want to negate is that for all x, p of x implies q of x. The negation of this implication is that you turn the universal quantifier for all into the existential. So you say that there is an x, and then we say that such that p of x and not q of x. So this is the equivalent statement of the negation. Another version of this, which we use a lot, the statement that has a set theoretical statement in it. So let's say that we want to negate that for all x. First of all, let me write it down with words. Let's say that we want to negate that if x is in set U, then something else is true. Let's say that q of x. Another way to write this down would be to say, this is equivalent to saying that for all x, x is in U implies Q of x statement. So here now this x is in U plays the role of P of x in the previous statement, the way we wrote it. Compare the two together. Looks different when we say that if x is in U, then Q of x. But in fact, you can write it the same way as before, with the universal quantifier. And then if you want to negate this, and you want to say that it's not true that if x is in U, then Q of x. So this would be equivalent to negating this statement with the quantifier for all x. X is in U implies Q of x. In our book, most of the time we see statement like if x is in U, then Q of x. We can combine these two together actually. For all x in U, we have Q of x. And then when we negate this, we change the universal quantifier to existential. There exists an x in U such that it's not true that we have Q of x. So let me write down then the parts of theorem 2.3.1 that has these statements. In theorem 2.3.1 there are three conditions. So the first one, U is not empty. This will be always satisfied. What I mentioned at the beginning of the class is that empty set is not interesting. So we're not going to work with such cases. So when you have to show that something is not a subspace, then only conditions 2 and 3 can fail. So condition 2 was that if UV is in U, these are vectors, then U plus V is in U. Another way to write this with quantifiers is that for all U in U, for all V in U, we have U plus V in U. Then if we want to negate this, the way we negate this, if we want to show that this is not true, then we want to show that the negation is true. We have to change all the universal quantifiers to existential. There is a U in U. Then we have to change and to or there is a V in U. Yeah, that's not supposed to be a vector notation there. Such that U plus V, and the negation is of that something being in U is that it's in not in U. All right, so notice the difference, and let me write this down with words. There exists U in set U, or there exists V vector in U such that U plus V is not in, the sum is not in U. So the important thing to notice here is that when you negate the universal quantifier, well, the universal quantifier must have this in notation. So when you negate it, you don't turn the in notation to not in. You just turn the universal into existential. Here in the implication at the end, we have that U plus V is in U, and when you negate the whole statement, that turns into not in. And also when we say that there exists something, and you want to show that this is true, you have to find it, if it exists. So you have to find at least one example. Since this example for the statement, this was actually statement 2. So this example is for the statement 2 to be not true. We call this counterexample. So we have to find a counterexample for a statement because we want to show that something is not true. That has a universal quantifier. So going to case 3 then, or item 3 that can fail in theorem 2.3.1, it says that if scalar A is in the scalar field F and U vector is in set U, then A times U is in the set U. With quantifiers, what it means is that for all A, since it doesn't specify what kind of A and what kind of U, then it's like an implicit way of saying that. Then that means that it must be true for all A in F and for all U vector in U. What we must have is that the product A times U is in U. Then the negation. If you want to show that this fails, then we have to show that the negation holds. The negation is true. So we say that it's not true that for all A in F and for all U in set U, we have AU is in U. Again, the universal quantifier changes into existential. There is an A in F or, and changes into or, then this universal also changes into existential. There is a U in U. When you negate this part, this last part turns into not in U. And that's the equivalent statement for the negation. And again, this is the case that if you want to show that this is true, that there exists, then you have to find examples. We will have a lot of these statements. You have to practice. I might give a separate logic assignment to practice these statements.